Hi, and welcome to a session. We are going to talk about monomial orders and how to use Python to compute Gröbner bases, but with different monomial orders that are available in SymPy. Now, before starting the session, I should say that I record these videos for some of my students, and it happens that time to time I have to repeat things again and again. So it's a good idea to record them and have them available. So in the next time I can refer them to the video, and I'm not going to become a YouTuber or anything like that. So you have to deal with or get along with not things not being perfect, such as my speaking or anything else. So this session has several assumptions. The first assumption is that whoever is coming to this video is already familiar with computational algebra or computational algebraic geometry. In specific, they should know what are multivariate polynomials, monomial orders, and the chances are that you are going to use these monomial orders for Gröbner basis computation. So I'm not going to define what are these things. Maybe here and there I mention a few things, but I'm not going to waste time on talking about them. If you don't know, there are some references in the description of the video, and you can go look at those books and references. The second assumption is that you already know about basics of Python. So I'm not going to tell you what is Python, how to do programming, where to write, how to run, what is if statement syntax, for loop, arrays, and those kinds of things. It's not for this video. And also, you know what is SymPy, because, well, the title of the video is how to define or use different monomial orders in SymPy for Python. So you should already know what is SymPy. SymPy is for symbolic computations in Python. And it just means you have variables, and your variables are not necessarily like the default normal variables in Python that store some value in them. They are just indeterminate objects, unknown objects. There is some, like the variables in math, right? People in physics or mathematics or algebra use these things, so this is something that those people are using. And lastly, I'm also assuming not all people that are familiar with the first three categories necessarily know about the fourth one. So if that is the case for you, you need to know a little about class, the object-oriented programming, and Python is one of the OOP language, right? There are some easy links I can put in the description. You can go and look at them. But I am assuming that you know already these four things. I'm not going to spend time on them, okay? So we are going to work with monomial orders. And when you have monomial order, it means you are in some polynomial ring. For example, the ring of polynomials in with n variables x1 to xn, and the coefficients are coming from the real numbers. That's the most common one, but you can have complex numbers, rationals, or other fields standing behind this square bracket. And x1 until xn can be x, y, z, or depending on how many variables you have, right? Then each polynomial is a linear combination of monomials, and each monomial is a product of some variables with some exponents. When you pick up a monomial, you can associate a vector of non-negative integers. It can be x to the power 1, or if, for example, x2 is not in this monomial, it means its exponent is 0, right? So you pick up the exponents, you put them in a vector, and this vector is of a fixed length of the number of variables in your polynomial ring. If something is not appearing, but that variable exists in your polynomial ring, you have to put 0 for its exponent there. So just be careful to not get trouble later and then saying what is wrong with my calculation, okay? So I have a monomial here. I can associate a vector, or the opposite. I have a vector of this length of non-negative integers. I can associate to it a monomial. Now, monomial orders are comparing monomials. It's putting an order between them. When you had only one variable, things were easy because you had x, so 1x, x squared, x cubed. The degree was enough to order your monomials. But when you have more than one variable, there are many different ways to order things. Okay? So one of the most known and commonly used monomial orders is called lexicographic monomial order. And that means you are looking like in a dictionary type of order. When the alphabet, you look at the first letter of the two words, the one that the first letter is more important, A, B, C. So A is greater than B, greater than C, right? So a word starting with A, say ant, A-N-T, is greater or coming sooner than a word starting with B, for example, bird, B-I-R-D, because the first thing, A is greater than B, right? And it's not completely same because in dictionary, it's not commutative. So ant and, I don't know, gnat are not the same, even though they have the same variables, you just change the order. But in polynomials, you can change the order in the product, so that's fine. It's a commutative ring here. So it's not completely same, but it is kind of similar. So lexicographic, what you do, you have two monomials, say, let's say this, so I'm in a ring with 4 variables, x1 until x4. And then for each of them, I associate a vector of length 4. x1 squared, so 2 come here, x2, 1 comes here, there is no x3 and x4, so 0 and 0. Then I have this monomial, every variable with exponent 1, so 1, 1, 1, 1. What does lexicographic order does is that it looks at the first entry of the 2 vector. Then it picks up the one that has bigger number. So 2 is greater than 1. This guy is the bigger guy, this one. And we are assuming that the order of the variables is the same as the order of the columns for these vectors if you write them like a row. So this is for x1 in both of them. This is for x2 in both of them. And we are putting x1 greater than x2. Okay. If the first entry for both of them was the same, 2 and 2, then we look at the second entry and compare them, and then we move forward. Okay? And if all of the entries are the same, they are just the same monomial. So we put equal sum between them. Okay? So that's the lexicographic monomial order. And the reason I'm talking about the vectors, well, it's a nice thing. You can see things clearly, more clear. But there is another reason too. It's good when you are working with a programming language or software. First, check how concepts are stored, how the data structure, what data structure they use. So in SymPy, monomials are the vector of exponents after fixing an order between the variables. That's important. So when in SymPy it is comparing these two monomials, it is not looking at them with the letters, the text that you're writing here. It's not comparing two strings. It is picking up these two vectors and it store them as tuple, and then look at the order here, decide which one is bigger, and then go back and tell you the monomial that is bigger. So that's important to get familiar with this kinds of notation if you are going to do some programming with SymPy in Python for polynomials and monomials. Okay. Now, lexicographic, which people usually show it with lex, is not the only monomial order. And in fact, if we go to homepage of SymPy and we go to the documentation page related to polynomial parts and search for monomial orders, we search monomial order, okay, not this one, but here you see there are lex order, graded lex order, reverse graded lexicographic. Well, usually people say graded reverse lexicographic, but anyway, they like to put it this way. So they have three named monomial order. And well, before continuing, one thing is the help page of SymPy Python are usually great, but sometimes it's too much text to write. They may just ignore, or they may not intend that part of the code to be used by their targeted audience or targeted users. So there is not much you can see about monomial orders here. That's one reason we have this video putting here. So yeah, but anyway, so going back, lexicographic is not the only monomial order. There are several other important ones: graded lex, graded reverse lexicographic. How are they defined? So when we write the vector of the exponents, looking at them one by one going forward works for lex, but will not work for graded lexicographic, because graded lexicographic first look at the total degree, and the total degree is summation of those exponents. Okay, so we have to change the input exponent vectors to another vector and then start comparing. How we can do that? Let's look at the lex. I can pick up the identity matrix and think about the lex this way: that if you give me the vector of the exponents as a column vector, I can multiply this matrix to that. The first entry will be the product of this row to that column, which simply says pick up the first entry. You check the first entry of the two exponent vectors, and the one with bigger, that's the winner. If they are equal, you look at the second row multiplied with those vectors, which says look at the second entry, and so on. So this is identity matrix. It gives you exactly the same vector that you had in the start. So that's the reason you didn't really need to bother looking at a matrix, product of a matrix and a vector, things like that. But now that we are going to other monomial orders, you need to do some more calculations. So the first number you are looking is the total degree, summation of the exponents of all vectors, all variables. That's same as saying the product of this row, which all are 1, with that vector. This is the first entry plus the second entry plus until the last entry, right? That's total degree. So you have a matrix, each row creates a new number for your vector of exponents, and then you start by looking at the first one, the second one, the third one. So this is the total degree, and the rest is the first variable, second variable, until last variable. So if the total degree of two monomials are the same, it breaks the tie with looking in a lex order. Okay. Now graded reverse lex says look at the total degree first, then don't use lex anymore. Look at the last variable, the least important one, and then the one with the smaller exponent, pick up that one as the winner. So if the last exponent for one of them is 2 and for another one is 3, if it was +1 here, it was saying that pick up the same 2 and 3, the bigger one is the winner, but we want the smaller one to be winner, so multiply by -1, it becomes -2 -3. Now -2 is greater than -3, so you can think about it as a lex order. After you multiply this to that vector, you get the total degree minus of the last exponent, minus of one before that, minus until the minus of first one, and then you go same way that you were going for the previous cases. You look at the first entry of the both vector, the one bigger, if equal, the second one, the one bigger winning, right? So that's the matrix way. Now a bit of more things. So for the lex, it is n times n, if n is number of variables, a square matrix. This one for graded lexicographic and graded reverse lexicographic is n plus 1 times n. It's not a square. It doesn't cause any problem, but you are doing something extra. If the total degree, the sum of exponents are the same, the first one until one before the last one are the same, for sure the last one will be the same. This is linearly redundant, right? So if up to here all the comparison conditions were the same, the last one will be the same, so there is no point of having that. So you could drop them, make them n times n, just ignoring the last guys. Before going further and showing you some calculations, one thing that you could notice from the help page of polynomials in SymPy is that the monomial ordering, you're only seeing lex, graded reverse lex. And is it all of the matrices, all of the monomial orders? Well, let me see if I have a page for that. Oh, okay. So that's not all the orders, and that's even more reason to have this video. For those three orders, I showed you 3 matrices, or 5 matrices, with the last row being there or not being there, that define those 3 monomial orders. Now, a natural question is, if I have a different matrix, different from those 5 matrices, such as this one, will it also define a monomial order? So I have a vector of 3 exponents, and I first look at the product of the first row with that vector. It gives me the sum of first and second vector. If the sum of the first 2 exponents of one vector was bigger than the other one, then he is the winner, that monomial is greater. If they are the same, I look at the second row, sum of the first and the third, and if it's still the same, I go to the last one, sum of second and third. Even look at more general case, I have a matrix M, and I put the entries from row 1, column 1 until row M, column N, and I put W because W is for weight. It is like I'm looking at a weighted sum of these exponents, giving them some weights, right? And then I have the vector of the exponents. Usually we use alpha 1, alpha n, but typing A is easier than typing alpha. If you're using LaTeX, you need to press more keys, right? So I use AIs. And then you create a new vector, a weighted vector. By multiplying this, you have M entries. And then you compare the first one, then second one until the end. So we can define many more monomial orders other than those 3. And I have an example here. So let's say you are in a range with 3 variables x, y, z, and you have 2 monomials, x squared, z squared, and x, y squared. So they give us 2 vectors, 2, there is no y, so 0, there is z2, 2. That's for the first monomial, and you can see easily the second vector will be 1, 2, 0. Okay. With lex x greater than y greater than z, I should look at the first entry, 2 is greater than 1, so x squared z squared is the greater one in this order. Now, with our new order defined by this matrix, we first convert these 2 vectors to 2 new weighted vectors. sum of the first two, 2, sum of first and third, 4, sum of the two and the second and the third, 2. So instead of looking at 2, 0, 2, I will look at 2, 4, 2. And for 1, 2, 0, sum of the first two, 3, then sum of 1 and 0, 1, sum of 2 and 0, 2. So instead of 1, 2, 3, 0, I look at 3, 1, 2. Now, I look at the first entry of these two, 3 is greater than 2. So the second monomial is greater in the order defined by this matrix, which is the opposite of what happened when I compared them using legs. And actually, even with graded legs and graded reverse legs, the first one should be bigger because the total degree is 4, but the total degree here is 3. So this monomial order is different from all those 3 monomial orders that are the most common one. And SymPy is more focusing on them. Now, what if I want to do a calculation, a Gröbner basis with respect to this monomial order? How can I do it in Python using SymPy? Okay, that's what we are going to answer. Now, one thing I always emphasize in my classes, because these days it's easy for some students and even some teachers of these students, these AIs like ChatGPT, Copilot, DeepSeek, and plenty more that are there or will come soon, no matter how advanced they become, it's not good for you to start learning things by them. If you are starting learning programming, if you are starting to learn computational algebra, never go to those things. It's same as an elementary school student learning basic arithmetic, adding a 2-digit by 2-digit number, 25 plus 36, and instead of practicing what the teacher hopefully was teaching at the class or he was reading in the book or whatever, he pick up his calculator, he knows how to press the keys on the calculator, plus and equal sign, and then get the answer right there. If he does that, if he uses calculator at that stage, it will end up later, maybe when you give him a 4-digit by 4-digit addition, it takes him half an hour or 1 hour at age 30, 40 to calculate, and then you think, well, what was wrong before in his education? Well, the wrong thing was using some tool that was supposed to speed up calculations for someone who has a lot of calculations and already know how these calculations work in theory. But he was using it at the stage of learning the concepts, and that's terrible. Now, these AIs, do not use them. And to help you to get a good understanding of these AIs, it is standing for artificial intelligence, but artificial intelligence does not mean ChatGPT, DeepSeek, or Copilot, etc. Those are some software, app, whatever, some bots that use some algorithms. The developer put some routines for them to do some search, to do some copy pasting, to change some of stuff, and sometimes some hard copy rules on them. If you want artificial intelligence in reality, means plenty of other things too. The code in a very simple game 30 years ago, 50 years ago, that is telling the enemy characters in the game how to behave, the chess computer player playing with you, the next movement, right? These things are also AI, artificial intelligence, pretending to do something like thinking of human. A better name for these AIs is automatic imitator, because they search either on online database or offline and pick up things similar to what you want, then create a new text that looks like the answer. Now, if you don't believe me, well, let's try. So here is an attempt of asking ChatGPT at a specific day, to be exact today, a bit before starting recording this video. The question is, how to use monomial orders in SymPy, how to access them. So it says you can access them by monomial order.compare. And there is a code here. There is a problem, and then he's saying some stuff. And there's also a second thing he's talking, and then third, plenty of things. Sorting a list of monomials. He understood that monomials are recorded as tuples of non-negative integers in SymPy. Well, that's good because, well, it reads the documentation and plenty of other things, some training data, blah, blah. And then it says something. So we copy paste these two codes in our editor. Let's start with the first one. And we run it. So let's run it. We get some error message. First of all, it says monomial order from this subpackage of SymPy takes no argument. That's the first mistake. It's just picking up stuff and write something that looks like an answer. You can also pick up the second code and run that one. Again, the same thing. Well, I looked at the documentation of this stuff. I know, well, indeed, it is not taking any input. Let's remove that. Let's see if it's fixed the problem. That's one problem it has. It says there is no .key method. There is no key method for a monomial order. So it introduced an instance of these things. We will see about them. And then it used this. The same problem happens here. There is no .compare method, but it looks like genuine. Do not use these things. Let me clear the terminal, close these useless guys. What is the better idea? Rather than the first attempt, when you encounter a question in your mind, going to some of these artificial imitator AIs, not the real AIs, typing your question and trying to copy paste from there. So I pick up 4 monomials. Before even doing Gröbner basis, let's do a simple thing, the comparison of the monomials. Which monomial is greater than the other one? I want to write a simple code doing this. So I have 4 monomials in a polynomial ring with 3 variables x, y, z. I'm picking up 2 monomial order legs and the new one that I defined by that matrix we saw a few seconds ago. With legs it's simple. You look at x is the biggest guy, 2, 1, 2, 0. So this will be the smallest guy. And then between these two, you look at the second important variable, y is 1, here is 0. So this is the biggest guy. This is the second guy. This is the third. This is fourth. Now with the other matrix defined monomial order, it's a bit of pain. You have to calculate the new vector. For this one will be the sum of the first two, x and y, 3. Sum of first and third, 2 plus 0, 2. Then y and z, 1. And I can do the same here, a bit of things. Do I have them here? No, but I wrote the answer, okay? But as I said, I want to have something automatic to check. So I'm going to VS Code. You may, if you are familiar with Maple, you know it's a software, math software with a very nice graphical user interface. You can think about it as a very cool calculator with a lot of advanced tools, taking integration, solving ordinary differential equations, doing Gröbner basis, etc. You expect to have that window open here and line by line calculations, but it might be interesting for some of you who haven't heard it before. Maple, you can do programming same as you do programming with Python. It has a programming language, and I can do it in the same way I write Python codes. So let me make a new file, monomial order, and I put M for Maple. Later I want to have monomial order P for Python, right? And the extension for Maple code files are MPL, some other things. I use here. I'm fine with that. And I already set up my VS Code so that I can run the Maple code here while I have Maple installed. If you are interested in knowing about Maple, I can put another video, but it's not important if you don't understand what is happening here. So I had those monomials, and colon equal. There is a different syntax for Python and Maple. I put them in a list. In Maple, the monomials I can still use as monomials instead of the tuple, the vector of things. If, remember the monomials is x square, and also in Maple you don't use double star, you use hat for exponent, times y. The second one is x times y square. Hopefully I remember them correctly. Y cube times z x square times z. I put a colon. That's something for Maple, just to make sure. Yeah, that's fine. That should be fine. Now I want to sort them, and I want to print the sort version of them. So print, could use semicolon instead of colon, and semicolon is this one, point and a colon below it to show the result. But it's a good practice when you are doing Maple code instead of Maple worksheet to use explicit print lines. I use the sort command to sort these monomials. Sometimes I have a typo when I talk, so I have to be careful. And then I have to give him a criteria, a Boolean function that receives two monomial and returns true if the first one is greater than the second one. So let's say m1, m2 are the inputs of this quick function, arrow, dash, and then greater than sign. And then from Gröbner package, so in Python I'm using SymPy package, in Maple I'm using Gröbner package, colon dash, and from that package I'm picking up the predefined function test order, and test order receive m1 and m2. It returns true if m1 is greater than m2 with respect to the order that you have to tell him. M1 lex, but in Maple lex is showed by plex, and P stands for pure, so pure lexicographic. Then you tell him x greater than y greater than z. Plex closed, test order closed, sort closed, print closed. Even though I'm putting colon, so it stop showing the compile or the running of that line, same as this one, because the explicit mention of print, there will be something in the terminal. So that's in this one. In Maple, the matrix defined monomial orders are defined automatically there. You can do them. Instead of plex, you say matrix in single quote with small m, and then you need the order of these three variables. But well, okay, we do that first, giving the matrix. So instead of using a Maple matrix object, we need to use list of list, and each sublist is a row. So 1 1 0 1 0 1 0 1 1. That's fine, but still it doesn't know the columns are related to x, y, z. I mean the order of them. Maybe it's y, x, z, right? So after closing the list of lists for the matrix, still inside the matrix, so before closing the parentheses for that, I give the list of variables x greater than y greater than z. So you notice that the first column is x, y, then z. Closing matrix, closing test order, closing sort, closing print. That should be enough if I don't have any typo or mistake. And then I can right click, maple runner. So the first line as I wrote, but the result is not being shown because of the colon. The second line shows it. It should not show because of colon, but I use print, so it shows. Says the smallest guy is x3z, that doesn't have x. Then the next guy is xy square, the one that has x with exponent 1, then the ones with exponent 2, and then the one with y is greater. See, so that's from a smaller to greater, same as what we saw in the notes in the PDF. And then using the matrix order, it shows these 4. So the smallest is this one. The sum of first and second entry, x and y, is 2 plus 0, 2. But for this one is 1 plus 2, 3, 0 plus 3, 3, 2 plus 1, 3. So these 3 are 3. They should be bigger than this one. And then you break tie with the second row and then the third row, right? So that's fine. I'm happy with these results. They are fine. They are correct. Then let's pick up an ideal generated by 2 polynomials in 3 variables, and I want to know their Gröbner basis with legs and the new monomial order. So I need to first define the list of polynomials. The first one was, let me look at it again, xy square y cube z minus x square z times y square plus y cube times z minus x cube times z, and then there is another one. Okay, the other one is y square x minus z cube. Y square times x minus z cube. Okay, that's fine. Now print from Gröbner package. Pick up the basis comment that calculates Gröbner basis. F, the list of polynomials, then the monomial order p legs x greater than y greater than z. P legs close, basis close, print close. Can copy paste this guy, then just change the monomial order with this. Hopefully I don't have any mistake. If I run it, I should see 2 more calculations here. Okay, so I got this one. In the PLEX, I have 1, 2, 3, 4 polynomials. With the new variable order, monomial order, I have 3 polynomials, and then these are maybe tiny for you, and then there is a star and hat, so I have them written more beautifully here. See, 12, 4 polynomials, 3 polynomials. Fine. Okay, so I have these calculations. I'm sure about the answers. I'm going to do the same thing using Python, right? So monomial order P for Python, and then the py, not py for Python. And of course, always write good comments, date, name of the person who wrote the code, some explanation what you want to do, but I'm skipping because it's a teaching session, so we need to somehow speed up. Now, I told you don't go ask those artificial imitators. Instead, go read the help page, the documentation of these things, right? So start reading these things and skip the parts that are not relevant to you. There are some other pages you can go through them. It takes a bit of time, but it's worth it. Or you can ask some other colleague, friend, classmate, teacher who knows about these things, and he can quickly explain to you. The difference is he's explaining something correct, and you are having conversation, you do some examples together, you're learning. You're not copy-pasting from somewhere. That's a different thing. And learning is important. And be sure many of your teachers are dreaming and loving that you go ask them questions. Okay? So, I need to have monomial orders. The default one, if I go back to that place, that was this one, are legs, graded, reverse legs, and you can see there are examples of using them. For example, sorting some monomial or monomials with respect to graded legs. So you know how to use these three, but how about the others? The explanation here, for some reason, the developers or the people who were writing the documentation were not in mood to write much, but they wrote some useful information. They wrote that monomial order is a class. And next order, graded next, and they are like child class of this parent class. And they put a link to the source. If you click here, you go to their GitHub page, and you can see the structure of these classes. That's very informative. You get a lot of information if you learned Python and about classes. If not, go and learn and then come back and look at this page. So, what we learn here? So, monomial order is a class. And indeed, it is not something from front page of the SymPy. So if I say from SymPy port everything, and then I'm going to define an instance of that monomial order class. So I say order 1 equal to monomial order. Okay, we experience from that fake artificial intelligence that this doesn't accept any input, and we indeed can see from here monomial order does not receive any input, because if it was going to receive an input, there would be an underscore init underscore method for it. Take some argument and put it as the attribute and stuff like that, right? But it is not. So monomial order doesn't accept anything inside. So that's the correct way of introducing an instance of this class. However, it's not accessible. It didn't detect it, and if I run it, it says some error. It's not defined. So I have to import it separately from, let's see where it is stored. It's inside SymPy polys ordering. Can also copy paste from here to here. We can memorize everyone from this place. Import monomial order. Now it is recognized, and if I run it, hopefully it shouldn't show any error message. It run with no error message. You see, that is the old one. This is the new one. There is no error message. I didn't ask anything to be done, just a new instance. But then how can I use this? So let's go back to the page of monomial orders. It has some attributes, some methods. The methods are not doing anything. You can call it on a monomial. This call means if you use that instance of a class, same as the way you were using a function. So we put its name, parentheses open, and then you put some argument. That argument is a monomial, but it returns an error message, not implemented error. Why? Well, this is a parent class. There are subclasses, actually 3 classes, and then there is another one, which is not what we want. I will tell you a little about it. Lex, graded lex, and reverse lex. So the child classes are instance of that class, but they themselves are a class. If there is a method here that exists in both parent and the child, an instance of the child class will do the method that is inside the child. So this call is like kind of overwriting this call. So if I call an instance of lex order version of monomial order, on a monomial, it returns that monomial back. If I call an instance of graded lex order of monomial order on a monomial, it put an integer that is sum of those numbers in that tuple of the monomial, and then the rest of the monomial. So it's doing same thing as that matrix product that we did. Okay, and then if we use the third one, it's picking the degree, the sum, and then the negative of the reverse, so the last entry of the monomial, and the negative of the one before the last until negative of the first one. Then it does everything in the lex style. So that's how it works. You can call them on an instance, but only this one, this one, this one. If you use monomial order without any specification, then you get an error message. So I need also to call lex order, and instead of this, lex order, and now I can call it on a tuple. So let's say print order 1. I give it 2, 1, 0. So hopefully no mistake. It should return the same thing back. Yes, it returned 2, 1, 0. Now the goal was not just using lex, graded reverse lex, but any monomial order that I want, specifically defined by the matrices. So I want to define a new class myself. In SymPy package, they have only those 3, and a product order, which is product of those 3, lex, graded reverse lex, which all monomials are not created in this way, right? So I want more freedom, so I have to create things myself. So I say a class, new class, m order is a new child class of monomial order. What do I need to put there? I need to redefine the call, otherwise I will get an error message. So def call, it has self and the monomial, same as what happened in these ones, right? And I want to return a tuple, and that tuple is sum of some product things of the matrix entries and the monomial entries. But then I need so I have monomial here, is a input tuple, but I don't have the matrix. So in contrary to Lex order, greater Lex order, reverse Lex order here in SymPy, that they didn't accept any argument, I need an argument because the matrix change for different monomial order defined by different matrices, right? And now I need an init method that even the parent monomial order didn't have it, to assign the attribute, the matrix. And just another thing, let's look at the attribute that these monomial orders have. There is alias, is global, is default. Is default is true only for the Lex order, and the other ones don't have it, so I don't need to keep it, because whenever it creates a new vector, it goes in a Lex style on that vector, so I don't want to destroy that. Is global is true for every monomial order they have. So for safety, I put is global there equal to 0 as an attribute. Maybe it's not necessary, I don't know, I will put it. And then we need that matrix. So here as a safety, I put is global equal to true. Maybe it's useless. I can put M for matrix and put none, and then in the init method I give value to it, but I don't need to do that. I can easily do it here. So when we define this, say self, a new attribute for self M being getting an assignment and the value, the M, the matrix. Now self M, that's the matrix, row I, and I'm saving this matrix not as a SymPy matrix object, it's just list of lists, same as in what happened in Maple. Then colon J multiply by monomial entry J for J in range, well, length of monomial, but to make my life easier, I put length of monomial in a variable n, and I say n. I'm going to use n again later. That's fine. So that's one row, the whole sum, which ends here. And then I want to repeat this sum for the next rows as well, for I in range in n. And I assume my matrix is square n times n. You could put some error messages that catching if the size of your matrix is not fine. For example, the number of columns is not the same as the number of entries in monomial, then it catches it and shows an error message. I'm not going to do that. I assume that the user always give a good M, good monomial, etc. That's fine. And now I will define a new instance of my own monomial order sub child class monomial order. I need to give the list of the rows of the weight matrix as an argument. So 1, 0, 1, 0, 1, and 1. Now I do the same. Monomial order 2. And it should give me 3, 2, 1, different from 2, 1, 0. Hopefully I didn't do any mistake. Let's see, I may have a mistake. And this tuple is important. You can try without the tuple. You get some weird thing when you type here. Should convert it to tuple. I have a okay, so the problem is easy. It shows the not implemented error. So that means the call is not rewritten, overwritten by this guy. That's my mistake of spelling. gb call, save this, and run it again. This time is fine. 210 with lex, 321 with a new order. So that's working fine. And let's do sorting. So the good thing is I have these maple outputs, so I don't need to go back to my slide or the PDF notes to remember the monomials. I have them here, monomials, but I give them as tuple because that's how SymPy working here. The first one is 2, 1, and 0, right? 2, 1, 0. 1, 2, 0, 0, 3, 1, 2, 0, 1. That's, and for sorting a list or some stuff, there are two choices you can have. There is this sort method for list you can use. I'm going to use the sorted function, and you have it will receive several arguments, the thing that you want to sort, the key, the criteria that it used to sort them from smaller to greater, or if you want from greater to smaller than this one, reverse, right? I'm going to use this kind of syntax. I go here, print sorted monomials, and then key equal. Now, should I write order 1? Well, no, because order receives one monomial and it returns a tuple, while we want something receive two things and returns true, false if one of them is greater than the other, right? So what can I use? Well, luckily, in the same code file that monomial orders in SymPy are defined, there is something called a monomial key. Again, it only receives these guys or the product ones. And one of the reasons I didn't use alias was that if you use alias, then it goes check the string thing, and the string is used for alias, because you see alias here for the lex, where it is being used is here when you want to print that instant as a string thing, then it uses the alias of the subclass that the instance is from them. And if you use the alias, then it check if where is it? Here. If those things are lex, greater reverse lex, otherwise it shows an error message. So I don't want that. I don't put any alias there. And I want these things to pass until it arrives here, then doing things. So I use monomial key. So I put monomial key, no alias in my class. That's fine. Here key equal to monomial key, and then I put order 1, and then again monomial key is not something in the front of the package, so I have to import it from this sub package, monomial key. Now it's fine. This is with the lex. As you can see, I don't need to use those lex and blah blah that, for example, you see here, they use monomial key, the alias, and then the list of variables. You really don't need that. If you have an instance of Lex order, you can just use the name. And more importantly, we want our order 2. So we need to receive 2 different versions of these lists corresponding to this line of maple and this line of maple, right? Hopefully no mistake. I save it, I run it, no mistake. So let's see, the greatest guy for both of them is 2, 1, 0, which means x squared y. In the output of maple for both of them, it was x squared y, correct? Then the smallest guy for Lex was y cubed z, all right? For the new monomial order is x squared z, that's correct. So we got the same output. Nice. So we can sort the monomials. Now the most important use is to use Gröbner. And if you pay attention, you have noticed I didn't define any symbolic variable yet, which is the essential part of SymPy, right? Now I'm going to use, because I'm going to write real polynomials with x, y, z. So Python should know what are x, y, z. So I write symbols x space y space z. So it doesn't ask what is the value of x, y, z because there are now symbolic x, y, z. Now my list of polynomials, another good news is that I can copy paste from here. C to V, and all I need to do, I did another extra square bracket. Okay, all I need is to replace these hats. So I press Alt key from my keyboard. I start clicking everywhere after all of the hats. There are plenty of other ways to do this. I do it this way. I press backspace, so I delete them. I press star. I did all of them at the same time. That's nice. This is now in Python syntax. Now say print Gröbner. If you don't know what is the command for Gröbner, it is computation. Gröbner. Read the documentation. It's very easy. Not this one. Should be a better one somewhere. Here. Yes. So Gröbner has list of polynomials. The variables, not in a list, just in order. It's a star argument. And then another argument which is for order. But I'm not going to use this alias things. I'm going to use it differently. So have Gröbner f my variables in order x greater than y greater than z, then order is a key argument, keyword argument equal to say order 1, simple. And the same thing for the second one, but let me not do the second one. So I just put it here too, but I comment it for some reason. Let's run this one first. I get this one. And 1, 2, 3, 4 polynomials, and then extra information how to read this guy, which is same as these 4 polynomials. But there is a nice thing about the output of Python is that the polynomials and monomials are ordered with respect to the order that you want when you request it. X squared z is greater than y cubed z and z cubed. But if you look at the output of Maple, this guy in fact is this one, and x squared z is in the middle, while you prefer it to be at the beginning. It's not a big deal because it's an order of which one you add first, doesn't matter, but it's more beautiful to have it this shape. So each of these two programming language have its own benefits and disadvantages. For example, Maper has the matrix defined monomial order already there. I didn't need to define a class or object for it. In Python, I need to define that myself, but the output is more beautiful, whatever. Now, why I commented this? Because I will encounter a problem, but let's encounter it. Never escape seeing error messages. It's not the end of the world. You will learn things from them. So I will run it. I will get an error message. If you look at this error message, it's about printing and say order equal percentage s for a string, and then he wants to put print version of that order. And if you look at the output of the first one, it says order equal lex, alias of that guy. Now we don't have, if we go back to the page of the SymPy code, when you print a monomial order, this string thing comes, it's called alias. These three guys have alias, so it prints the lex from the lex order. Now we don't have that, and if I put the alias, it will cause problem with the monomial key things. I don't want to cause that. So is it the end of the world? No, I just force to rewrite this string thing for my child class. So I add a different method here, def underscore underscore str underscore underscore self. Now I can have this matrix M also coming in and print. So here, instead of lex, I say matrix defined with this matrix blah blah blah. But the matrix can be so long sometimes, so it's better to save space. It's already long, and the Gröbner basis can be long itself too. So I just say return a very small size string, it says matrix defined. So I don't need to worry what is the value of M. For all of the matrix defined, says the matrix defined. Now if I save it and I run it, I don't get an error message, and I have 1, 2, 3 polynomials, which are same as this one. Z cube xy square is this guy, and that's fine. It says matrix defined. So I successfully defined a different monomial order in SymPy, and in my code file you could go and edit the place that these SymPy packages is stored. I think the developers, you can check the homepage of SymPy, gave permission to edit their code. Always check these permissions, never skip them. Sometimes it can be very important, the licenses. But here you see the address where these files are stored. So you have a copy of this GitHub code file on your computer. You can go there, add your monomial order officially in your computer, so not repeating it in each individual files, but also you can do it outside. And it works pretty fine with monomial key for sorting them and with Gröbner. Maybe for another command in SymPy that you're going to use later, I don't know, some division or whatever, you may need to add or change some of these methods. You can do it. Now you learned how to do these things. So you don't need to go to ChatGPT. You don't need to be worried. You can look at the documentation, look at the code source of the code files, source of the code, and play with things and make things work for yourself. So we get that. And just one thing to clarify, because sometimes I also forget it. One question. Lex, graded lex, graded reverse legs were defined by matrix. I pick up another matrix and I define a monomial order. Is it true that all matrices define monomial orders? Well, we should be careful. So remember the graded reverse legs was 1, 1, 1, 1, and then -1 in the opposite of the diagonal. Now, if I remove that 1 and pick up this, is n times n, is full rank. Looks like should be defining a monomial order, right? But be careful. If I pick up the last variable or any other variable, I consider their exponents, exponent 0, 1, 2, so on. The vectors that I receive after multiplying this matrix to it will be 0 for everything because they're not there. So these guys are useless. And then, well, okay, the rest are, well, okay, there is a typo from here. I have to put this -1 at the beginning. So it will be 0, 0, 0, 0, -1, 0, 0, 0, -2, 0, 0, 0. And then you look at them, because 0 is greater than -1, then it suggests that 1 is greater than xn, greater than xn2, and the sequence is getting smaller. If you learned monomial orders properly from the textbook or from your teacher, monomial orders have several properties. Not every order is a monomial order. And one of the important one is every non-empty set of monomials should have the smallest member. And in general, one should be smaller than every other monomials in general. But here we have the opposite. A sequence increasing, growing more and more is fine, but decreasing more and more, smaller, smaller is not fine. And one being greater than others is also not fine. So this is not a monomial order. Now, looking at your textbook, for example, the standard computational algebra geometry books written by David Cox, John Little, and Donald O'Shea, which are standard. One of them is ideals, varieties, and algorithms. The other one is using algebraic geometry. Both of them have monomial orders and Gröbner bases. In this one of the exercises, it says, let M be an M times N real matrix with non-negative entries if the kernel of M intersection with the vectors of integer entries, integer valued vectors, is only the vector of zeros, one element there, then the order defined by that matrix is a monomial order. And also a little before that, it says if entries of M are rational numbers, not necessarily any real numbers, just rationals, then this condition tells us that M should be greater than or equal to N, and M should have full rank. So you can restrict to M times N positive rational entries, matrices. Those are safe to work with. Otherwise, you may end up with problems such as the above one. And for graded reverse legs, you may say, okay, if the negative ones are bad and I have to restrict myself with the positive rational entries, will I miss something? Well, no, because this guy is equivalent. I mean, the order defined by this guy is same as the order defined by this one. If the sum of the exponents are the same, the least one being smaller is same as the sum of the others except that guy being greater, right? And that's where I picked up my example 110, 101, and 011. And because I didn't have this 1111 at the top, I had to include the last one, 0111, to get a full rank, right? So that's something to keep in your mind. Well, I hope it was useful, both from mathematical aspect and also from programming with Python, maybe Maple as well. That's all, but I put something else. If you are here interested in algebra and algorithms, and therefore combination of these two, the chances are you will be interested in future algorithms conference. This year is 2025, but if you are watching in next year's 2026, 2027, they should have more button or updated version. You can click there and check out what is this conference about. I'm not going to talk about it or giving advertisement. If you are interested, you will go check this page, and hopefully you will find it useful.